the room, go to the diner this evening. The rest of you are welcome to think about us while we're at the diner, or join us if you are local. But other than that, I will now close what month is this? October meeting of MHAA. And thank you all for attending the first virtual session. I'll now hand it over to Alex to introduce our speaker for the evening.
Okay. Dr. Sam Grunblatt is our presenter tonight. He's I hope I'm pronouncing this right, Kalbfleisch postdoctoral fellow in the astrophysics department of the American Museum of Natural History and a guest researcher at the Simons Foundation Center for Computational Astrophysics. Sam was born and raised in Kingston, New York, and graduated from Kingston High School in 2009. From there, he obtained his BA in astrophysics from Columbia University in 2013 and his PhD in astronomy from the University of Hawaii in 2019. Sam's research focuses on detecting and characterizing planets around red giant stars and measuring the oscillations of those stars to determine their internal structure. Outside of the office, Sam enjoys making music, attempting to surf, and lately has been hiking and camping in the Hudson Valley to rediscover the stars that first captured his imagination as a child. Okay, take it away.
All right. Well, thank you all very much. Thanks for that great introduction. And yeah, it's really exciting for me to be here and talk to you folks. As a former amateur astronomer of the Mid-Hudson Valley, it's really cool to now come back and talk about what I've been able to do since I made that less of a hobby and more of a profession. Okay, so I'm just going to go ahead and take it away from here. Can everyone see my slides okay? Okay, great. Looks like I'm getting some nods. All right, so yeah, over most of my professional career, I've basically been dealing with systems that kind of look like this one, which this looks cool, but I think if you really want to capture the the essence of what's going on, I think this cartoon does an even better job of what I'm going to be talking about today, which is these poor little planets that are getting lured in closer and closer by their host stars in a scenario that, as you can imagine, does not end very well for the planets. But before I get into all of the details of that, I just want to give some quick background on stellar evolution. So this is stellar evolution in 30 seconds. So here, basically, every star starts out as a sort of protostar core, which you can see here on the left, some of which might eventually turn into planets. But for this talk, we're going to focus on the sun-like stars, which are in the center of this figure. And these sun-like protostars will then evolve into main sequence stars, and they remain main sequence stars, like the sun, for example, for around 90% of their lifetime. But then in the last 10%, they get progressively cooler and larger, turning into red giants and then red supergiants. And then eventually they actually blow off most of that material and leave behind a white dwarf. And so since supergiant stars are actually larger than the orbit of the Earth, which means that the Earth would be inside of a supergiant star if the sun was a supergiant. That means that somewhere between the main sequence and the supergiant phase, these planets must get swallowed up like that cartoon was showing, or they get pushed to larger orbital distances. And so we wanted to determine if we could, see how the planet population actually changes from the main sequence to this red giant and then eventually red supergiant and white dwarf phase. But of course, in order to do that, we need to be able to detect these planets orbiting other stars. And so the vast majority of planets that have been detected outside of our solar system were found in two general ways, using either the radial velocity or the transit methods. And so the radial velocity method detects the wobble of a star as a redshift or blueshift, redshift and blueshift of its light as the planet pulls on the star in its orbit, and that tells us the relative masses of the planet and the star. And that's shown on the left here. And then on the right, we have the transit method, which is similarly sort of reliant on looking at the star. And then as the planet passes in between us and the star, we see this regular symmetric dimming of the host star, which we call a transit, and then use that to determine the relative star and planet radius. And so we have the planet mass, we have the planet radius. Now we can start to say something about the whole population. And of course, it would be almost impossible to talk about planet detection without talking about Kepler. The NASA Kepler mission was probably the most successful planet hunting mission to date, or it definitely was the most successful planet hunting mission to date. Kepler was a space telescope that was launched in 2009, which stared at over 100,000 stars in one patch of sky for over 4 years to detect transiting planets around them. And Kepler was super successful. So on the left, you're seeing basically all of the planets that we knew of without Kepler, even including planets that were found via transit, but with other surveys. And you can see that when we look on the right, where we do have Kepler planets in yellow, it's completely changed the number of planets we've been able to detect. It's revolutionized the detection of small planets. So anything smaller than basically Earth or Neptune size is thanks to Kepler. But it's also sensitive to an even wider range of previously known planet populations. So we're getting not only really short period planets with Kepler, but also planets at orbits almost as long as the Earth is on. And so it's really good for planet occurrence determinations. And so that was one of the first things that Kepler actually looked at, was trying to study planets around sun-like stars. And so if you look at the stars that were targeted by the Kepler Prime mission, you can see that basically the majority of its stars are at that red center place. Can people see my cursor if I go like this? Okay, great. Yeah, so this is sort of the bulk of the planets that were found by Kepler. They're all right there, the very sun-like stars. And so that was basically because Kepler was trying to figure out how many Earth-like planets there are around sun-like stars. And so it was essentially able to get really close to that using 4 years of observations of one area of the sky. But in 2014, Kepler could no longer point at one area of the sky continuously. One of its gyroscope wheels broke, basically. And so from there, they started the K2 mission. So K2 was basically a similar mission, but instead of observing the same patch of sky for 4 years straight, it observed these different patches every 80 days. But one of the things that was different between Kepler and K2 is that K2 also had community-chosen targets. And so unlike Kepler, it didn't have to focus so heavily on these sun-like stars. In fact, it was able to observe a lot more giant stars. So you can see that both down here, which are the M dwarfs, these are really small stars, but also up here, these giant stars were observed a lot more commonly than with Kepler. And so that meant that we could start to investigate new areas of exoplanet demographics and start to look at things like the relation between planet occurrence and stellar mass, or the effects of the evolution of stars on these planet properties. And so just to put this kind of in context, less than a decade ago, there were actually no planets that were known on short period orbits around evolved stars. And so basically people just assumed that all of these planets, the red dots out here, were sort of things that had survived at late times around these evolved stars. But internal to here, the idea was that all the planets either got engulfed or sort of fell into their host stars. But with K2, we were able to change that. Thanks to K2, we actually found a handful of planetary systems on these short orbits around evolved stars. But we still didn't know about a lot of them. These evolved systems still remain pretty poorly understood. So why should we even focus on these planets at all? Why should we look for planets transiting giant stars? And I'll try and sort of break down the reasons I'm most excited about, but hopefully I can convince you guys that they're exciting by the end of this talk as well. And so one of the first things that's really great about these systems is they let you, or they allowed to answer a problem in exoplanet science that's been debated since planets were first discovered more than 20 years ago, which is the mystery of planet inflation. And so basically, we know that gas giant planets that are really hot, much hotter than Jupiter, can become inflated to sizes that are larger than our models would expect. And we have kind of two classes of the mechanisms that can cause this inflation. In class one, a fraction of the stellar irradiance, so the stellar heat and light, is deposited directly into the planet's interior, and that causes the planet to become inflated as the star evolves. Whereas in class two mechanisms for inflation, basically the planet is inflated when it initially forms, but then the heat from the star can't penetrate deep into the interior. It merely keeps the planet with that initial heat, slowing the cooling of that planet. And so in order to sort of pin down which of these two classes of mechanisms we're seeing, we could ask, how do we actually distinguish between these? And so if you imagine a hot Jupiter that's orbiting a main sequence star, as the star evolves and gets larger, the irradiation, or the amount of heat and light that planet is receiving, changes. And so by the time the star is a red giant, if these class one inflation mechanisms are correct, the planet will get re-inflated. It'll look very, very large again. But if these class two mechanisms are correct, this planet won't respond to the change in the star, and it'll basically maintain its uninflated size. And so the only way to test this sort of re-inflation hypothesis, distinguish between these two classes, is to study the planet population of these evolved stars. And so that's something that I did for my PhD thesis at the University of Hawaii. So here's just a plot of planet radius versus age for K297b. This is one of the first planets that was found transiting an evolved host star. And these colored lines are basically correspond to different potential heating efficiencies that allow the planet to become re-inflated at late times, whereas that black curve is one where the planet doesn't re-inflate. It merely has delayed cooling. That's the class two mechanism. And so now I've added another Kepler planet to this plot, which is a planet that has a similar mass and orbital period that's orbiting a similar mass star that's still on the main sequence. It hasn't evolved into a red giant. And what we see is that the radius of that planet is significantly smaller than the one I found, which suggests that it is this post-main sequence evolution, the star becoming a red giant, that's causing the planet to puff up similarly. So that's telling us that these class one re-inflation mechanisms are probably correct. And we can finally distinguish between these two inflation mechanisms after 20 years of knowing about them. But inflation is actually not the only aspect of this sort of planetary dynamics that these evolved systems, these red giant systems, can constrain. And so the population of planets around red giant stars can also tell us about how planet orbits change during planet evolution. And we can then use that information to understand how planets and stars interact and basically the timescales at which that interaction happens. And so here's an example of that. So this is just a plot of planet eccentricity, the orbit eccentricity versus the period of the planet for a lot of giant planets, so larger than 0.4 times the size of Jupiter, where the red planets are those evolved systems and the black points are dwarf systems or main sequence systems. And essentially the important thing that I'm trying to show here is that if we focus only on the left side of this plot, so the planets with the shortest period orbits, we find that for these evolved systems, we have a median eccentricity of around 0.15, which is not huge, but it's not nothing. So there's a little bit of eccentricity in these planets' orbits. But if we look around the main sequence stars, we find an eccentricity of only 0.06. It's considerably smaller. Most of those planets are on circular orbits. And so we can basically use that to then try and determine the speed at which these planets are spiraling into their host stars and also circularizing, going from eccentric to circular orbits. And these timescales, I'm not going to explain this equation, but what I will point out are these two factors here, which are the tidal quality factors, Q star and Q planet. And you can think of these as describing the squishiness of the star and the squishiness of the planet. And so we can basically assume the literature values for these and determine how fast these planets should be inspiraling and circularizing in their orbits. And so what we see is that the inspiral and circularization timescale for these evolved systems are pretty similar, but that the inspiral timescale is actually shorter. And so that means that what we're probably going to see is that these planets are essentially circularizing in their orbits, but also spiraling into their host stars. And so even when they're at short periods, they're still not on perfectly circular orbits the way that a lot of these dwarf star systems are. And so we think we're seeing orbital migration that's driven by this star getting larger. And so in other words, we think that these giant stars are squishier, and that's basically the evolution path that we're seeing that's differing between giant stars and dwarf stars. Okay, so the evolution of a star off of the main sequence is probably affecting the surrounding planets pretty strongly. And so that should cause changes in the population of these planets. And so we wanted to know, can we actually measure this? You know, how long can these planets survive around these rapidly evolving host stars? And so here, I've plotted planet occurrence, or the maximum possible planet occurrence, around these low luminosity red giant stars as a function of planet radius and period. So this was kind of one of the main results from my PhD thesis. And so all of the estimates in this box are upper limits, with the exception of this like upper leftmost box. So those are the hot Jupiters, which is the only region of parameter space where true planets were detected. And so I then also put the main sequence, or so the dwarf star occurrence rates in parentheses for each box. And so every place where we could actually have a chance of detecting planets is clear, where the things that have diagonal lines to them, we basically didn't have completeness there. We couldn't have detected those around red giant stars. And so if we focus specifically on these short period planets, so things that have orbital periods of 10 days or less, what we can do is essentially show, if we look at planet occurrence versus planet radius for main sequence stars, what we see is that it looks like planet occurrence seems to decrease with radius around main sequence stars. You see mostly, hot like Earths. Then you see a smaller number of Neptunes, and from there, a smaller number of Jupiters. But based on our survey of these low luminosity red giant stars, these evolved systems, we can say that it actually seems to be in the opposite direction, that planet occurrence seems to increase with radius when we look at these evolved systems. I'll note again that we couldn't really say anything about the smallest planets here. We weren't sensitive to them. But for the planets that we could detect, we detect this unique sort of trend for these evolved star systems. And that prompted us to, investigate, where did these planets actually come from? And this is something that first, for my PhD thesis, like I said, with K2, we could do a little bit of this, but we couldn't do a whole lot. As you can see, all of our results are essentially based off of the three points that you see on this plot. And so even though this almost doubled the number of planets that we knew transiting these evolved stars, there was still a lot more that we could hope to get to, actually try and understand these populations. And so in order to do that, we move forward with the NASA TESS mission. And so we can do a lot better now, thanks to TESS. So TESS is actually surveying the entire sky to search for transiting planets around bright stars. And so TESS is getting 30-minute cadence full frame images of the entire sky, which means that unlike Kepler, which was focused on specific targets, we can actually go and download images of the entire sky and then just pick out which targets we're particularly interested in. So in my case, that's giant stars, and focus on those stars specifically and just get observations for them anywhere in the sky in a way that we couldn't with Kepler or K2. And so that really means that the potential number of stars where we can search for these things, these planets, has absolutely exploded. And so to just sort of show this graphically, this is a plot of planet radius versus orbital period for all of the confirmed planets that we knew of transiting evolved stars pre-TESS. And so half of the planets on this plot are from my thesis. That was exciting, but there's just not that much that you can say when you have fewer than 10 planets to study. And so here's what we found in the first 2 years of the TESS mission. And so now we've effectively confirmed 4 more planets. So essentially almost doubling the number of planets around evolved stars again. Those are the big red stars on this plot. but we're hoping to get much further with all of the purple stars as well. Hopefully very soon we'll have literally more than doubled the number of planets around these stars. And beyond that, there are still all of these littler red and gray dots, which are sort of objects of interest and candidates that I've personally flagged that haven't been observed at all. And so TESS is really going to transform our ability to do population level studies of this evolved planet population and compare it directly to the main sequence stars. And so just a quick shout out to my student or a student I've been working with, Nick Saunders, who's really the reason we've been able to do this so well. So Nick is an NSF graduate fellow at the University of Hawaii right now. And he's been working on basically turning these full frame images into light curves, which we can actually search for planets using this sort of flow chart that I've shown here. He's built a pipeline called Giants, which basically downloads the full frame image data, then makes a cutout around the target that we're interested in, stitches together all of the available data for that particular target, and then smooths and cleans that light curve so that we can actually look for planet transits. And just to give you an idea of how well this is doing, I'm not going to explain everything in this plot, but basically the main point is this is a comparison of 4 different pipelines, which have all been produced to produce light curves from the TESS full frame image data. And our light curve is basically the red one, which is on top. So that light curve seems to have the lowest scatter out of all 4 that we're showing here, including even one that was designed by like a very large team of people at MIT. But because they're not focused on the red giant stars, we're really able to optimize our light curves using this sort of lightweight process to find planets that are getting missed by all of these other surveys because they haven't been optimized for these stars. And so this pipeline is really great at not only finding planets around red giant stars, but just more generally finding low signal to noise ratio events. And so we're hoping that maybe in the future, people can even use this to search for Earth-like planets around sun-like stars. That particular planet, Nick was actually able to publish or is in the process of publishing right now. And so one thing that's really interesting about this particular planet is that even though it seems to be orbiting this evolved star, it actually doesn't appear to be inflated, unlike the planets we found K2. And so the plot on the left is basically showing planet mass versus radius, where the different models for planet composition are shown by those colored lines. And though a lot of the planets that we actually observe lie above those lines, this planet does not. So that makes it kind of interesting. It's a non-inflated planet. And furthermore, when we look on the right, which is a plot of planet radius versus incident flux, so the amount of light that the planet is receiving from its host star, we see that this planet is kind of an outlier from this trend. It's shown here in pink. And this planet is actually unusually small for the amount of incident flux that it's receiving. It's getting over 1,000 times the light from its host star that we get here on Earth. But the planet doesn't seem to be following this sort of larger trend of planets where you see that they become larger when they get larger or higher incident radiation. And so we think this actually might be related to the evolutionary state of the system. So here I'm basically showing all of the planet host stars that we know of from TESS. And then the curves on this plot are showing different evolutionary tracks, where all of those tracks where they sort of come together on the upper right. So up here, if you can see my cursor, that's when the stars become red giants. And so you can see that our star here in orange hasn't actually become a red giant yet. It's still sort of a subgiant star. So it's more evolved than the sun, but it's not as evolved as some of these other systems. And so it's possible that basically the system hasn't been evolved for long enough to actually undergo this reinflation that caused these other planets to become that much larger. And so this actually is supported by some other studies that suggest that this reinflation process is something that happens really quickly. And it turns on only when you hit the red giant branch. And so this is something that we're hoping to test now with our larger study or our larger sample of TESS stars. And so that's essentially what I'm showing here. This is the next 3 planets that we found in our survey with Tess. And unfortunately, the picture isn't quite as clear as we had hoped. So the systems don't really show the same correlation between evolutionary stage and planet radius. So we were hoping that sort of like the stars that were in the upper right of this plot on the left would also be on the upper right of the plot on the right. And as you can see, that's not necessarily the case. And so these correlations between planet inflation and evolutionary state depend on a lot of things, not only the amount of incident flux the planet's receiving, but also like the planet mass, the stellar mass, things like that. And so we really needed a larger sample of planet masses before we can sort of test this at the population level. But luckily, thanks to Tess, we're actually getting those planet masses now. And so again, with more than 5 times the planet candidates known previously, and by doubling the number of planets that we can actually confirm, we can get lots of masses for these systems and start to actually investigate these things. And so in order to do that, we're basically using telescopes here on the ground, but all over the world. And so here I've listed the different spectrographs that we've used so far to get these mass measurements of these planet candidates. And I think at this point, we have telescopes on 4 different continents that we've used with the different instruments that are all shown on this slide. But the majority of those measurements are coming from Keck High-Res, which is the telescope shown on top, which are on Mauna Kea in Hawaii. So they're telescopes that I'm pretty familiar with, thanks to my graduate school. Okay, so to just kind of highlight the new systems, the 3 systems here on the left are basically the ones I was just showing you. They all have pretty clear orbits. They look to be circular, and they're also on really short orbits. You'll notice that their periods, which I think are listed, are around 3 to 6 days. So these are the shortest period planets we've ever found around evolved stars. They're the hottest Jupiters that we found surviving at these late times. But not all of our systems look like that. So here's like 3 kind of weirdos, as I like to call them. You can see that their orbits aren't so perfectly sinusoidal, so they're not circular. And they're not all kind of at these really short periods. We have a wider range of planet periods, and also a wide range of planet masses. So the least massive planet here is like 20 times the mass of the Earth, whereas the most massive planet is more than 100 times that. It's like 2 times the mass of Jupiter. So we're spanning a pretty wide range. We can start to think about those population level statistics for the first time. And here's also some more planets that we've been finding thanks to Tess. So this is some work that I've been doing with a grad student at the University of Porto in Portugal. And so these are actually targets that we weren't able to get to with the Keck telescope. These are targets in the southern hemisphere. And unfortunately, we weren't able to get as precise mass estimates as we did with Keck. But we've been able to confirm these systems, and they look pretty interesting as well. We see one looks to be eccentric, the other one doesn't look to be eccentric. One, we need more data. So this is a work in progress, but it seems to be panning out pretty excitingly. And we can actually get to the point now where we can say these, look into these population level effects. Okay, so just coming back to this plot of planet eccentricity and sort of talking about how these planets spiral into that host star as they get closer and closer to that mean looking star that's trying to lure them in that cartoon I showed. And what we find is that if we add these new systems now to this plot, so they're shown all as these brighter red stars that I just added, they lie right on top of where we'd expect based on the other planets around giant stars that we found so far. And so this is pretty good evidence for what I was saying before, that these giant stars are squishy, which means that the in-spiral of these planets is happening on roughly the same timescale as their circularization. So that means that these planets are both moving to smaller and smaller orbital periods and to smaller eccentricities at the same time. But it's not like one gets there much faster than the other. Whereas for dwarf stars or sun-like stars, the stars are very stiff. And so what happens is your in-spiral timescale is much shorter than your circularization timescale. So that means that planets can either circularize, so they move down very quickly on this plot, or they basically stay at whatever eccentricity they have been for their entire life. And so this does seem to fit into our kind of earlier picture that sun-like stars are stiff, giant stars are squishy, and these planets around giant stars are becoming less eccentric at the same time as they're basically falling into these host stars. Okay, so now that we've got a population of these evolved transiting systems, we can try to explore these population-wide trends compared to the known planet population around more sun-like stars. And so this is just a plot of planet mass versus radius for all confirmed planets with radii larger than half a Jupiter radius and periods shorter than 10 days. And so the planets found by this survey are shown by the black stars, whereas our other evolved K2 planets are shown by the kind of gray, less opaque stars. And what you see here is that there seems to be maybe an anti-correlation between the planet mass and radius as you move from the upper left-hand corner to the lower right-hand corner, that you see the black stars move that way in a way that the blue points are not. And that sort of goes with what we'd expect. So if we look at this in a slightly different stretch, it appears that if you get to like higher and higher masses, you see that there are a lot of blue points left over at masses greater than 2 times that of Jupiter, 10 times that of Jupiter, where we're not seeing planets around evolved stars. And that implies that these more massive hot Jupiters are getting engulfed, getting swallowed up most quickly, which is what we were expecting for these evolved stars, and would explain why earlier surveys basically assumed that these planets didn't exist at short periods. Early surveys were only sensitive to the most massive planets, and so they just didn't find them. But now that we're sensitive to these lower mass planets, we're starting to see that they are there. They're just lower mass than what we initially expected. So now moving to this radius versus incident flux plane, here I've added more of these new test systems as dots that are now have stars around them. And so you can see that for our evolved systems, it seems that in general, all of them are kind of on the lower envelope of this distribution of giant planet radii for a given incident flux. And so that implies that these planets, they are being heated, they are getting reinflated, like we said before, but it's possible that this reinflation mechanism is actually not as strong or not as efficient as the initial inflation mechanism. And that kind of makes sense. It's very easy to hold on to the heat of the planet. It's much harder to put that heat back into the planet and reinflate it at late times. And it might also be telling us that the time scale for inflation is pretty short, or for reinflation is pretty short. That if these planets hung around for a really long time, they might get pushed up on this plot. But because they have limited time, again, the planet's about to swallow them up. When we actually see them, they're still at the lower end of this distribution. Okay, so the evolution of the star off of the main sequence is probably affecting these surrounding planetary systems pretty strongly. And so that we can see that, you know, if we look at these systems, that there's still a lot of work to be done in terms of understanding the distribution of masses and things like that. But we do seem to have some differences that seem to actually be popping out, which is really exciting. But now I just wanted to sort of transition to one kind of final discussion that I think is really exciting, which is using these systems to actually try and find planets at the farthest distances within our galaxy, and potentially even detect planets of extragalactic origin. Okay. So in order to find planets of extragalactic origin, what you can do is look at the relative motion of the planet's host star relative to the sun. And so that's what this plot is showing. So basically, concentric circles on this plot are moving further and further away from a velocity that's very similar to the sun, which is generally what we expect for planets that are in our own galaxy. Most of them are in the disk of the galaxy and have very similar motions. And about a year ago, the first planet that's probably from a different population, so in this case, the thick disk of the galaxy, was found, and that's the red star on this plot. And one of the reasons they were able to show this target was so interesting was that its velocity is markedly different than what we're seeing for our own sun. As you can see, it's pretty far out in these like concentric circles. And I think there are some other aspects of this planet, probably also the distance or location of where it was, that led us to believe that this is probably a planet that's not from our own like local region, but from further out in our galaxy. And so going even further than that, if we think about the larger structures within our own galaxy, those can actually show evidence of early mergers between our galaxy and other galaxies. And so thanks to the Gaia satellite, which was launched in 2018, we now have velocities of these stars, not only in our own galaxy, but even, or they're not only in the plane of our galaxy, but also in the galactic halo as well. And that's sort of what's being shown here on the left. So all of these different arrows are corresponding to a particular population called the Gaia Enceladus group, which is thought to be stars that were from another galaxy that then merged with our own galaxy early on in its history. And now those stars have basically spread out all across our galaxy. But if you look at their motions and their compositions, you can tell that they actually came from a different galaxy. And so together with one of my students, we've been basically taking the targets that we've been looking at to study the substructure in more detail. And so by using the motions of these stars from the Gaia satellite, which I'm showing on the right here, we could basically cut out a region that was closest to our sun. So basically the kind of lower right triangle there corresponds to the sun on the previous plot, and just removed all of those stars so that we only left those stars that had very weird motions so that they were more likely to be part of the galactic halo. And what we did is then search to see, one, if we can find any planets around those stars, and two, just to understand how sensitive those planets or those stars were to planet being detected in them. And so in order to do that, we did an injection recovery test to determine the sensitivity to and the occurrence rate of these planets. So this is just showing on the left a test light curve of one of these stars in our sample. And then on the right, after we've injected a planet transit into that light curve. And so you can see there are sort of these periodic dips that you see that you don't see, that you see on the right that you don't see on the left. And we then tried to recover those systems by basically doing a search for planets in all of that data. And if we found that the planet radius and the transit depth matched well with what we injected, then we consider that planet recovered. And so although we weren't able to detect a lot of these planets around all of these stars, we could detect, again, the shortest period planets that were the largest, so these hot Jupiters. And we were able to show this on the right. This is our completeness of our survey. We recovered more than 60% of all of the hot Jupiters that we injected, even though we couldn't recover that many other planets. And so this let us place upper limits on the occurrence rates of these hot Jupiters around these halo stars that were observed by TESS. And so that's basically what we're showing here. These are, we weren't able to detect any planets in this sample, unfortunately, but we were able to place upper limits that sort of agree with what we'd expect. And we also were able to determine or predict at least what number of stars needed to be searched with a similar level of precision to find a planet with an extragalactic origin, which I would be really excited about. But based on this work, I'm not too surprised it hasn't happened yet. Basically, the unique chemical composition and the relative faintness of these stars makes it really hard to discover even hot Jupiters around them. And so we predict that we're going to have to search closer to 50,000 of these stars, whereas for this study, we searched closer to like 1,100. Okay, so in summary, TRESS has really like revolutionized our ability to find these evolved transiting planets, and like ground-based surveys such as Keck are making it possible to now compare these planets to main sequence systems, to dwarf stars at a population level for the first time. And so now we can see that these planets are in fact inflated, but they're not as inflated as similar planets around main sequence stars. In addition, these planets are pretty low mass, which explains why it took so long to find these planets. We weren't sensitive to them until relatively recently. And so continued follow-up with the TESS survey, as well as ground-based facilities, will constrain the dynamics of all of these systems and teach us more about how these planetary systems evolve, and eventually the planets get engulfed and they die. And it even has a potential to teach us about this extragalactic planet population, as I'm showing here with a little diagram on the right. And so, yeah, that's all I had. Thanks very much for listening. And if folks have any questions, I'm happy to take them now.
All right, thank you. Wow. Hope you heard the applause in the room, but I think I had most of the mics muted. Do we have any questions? Any questions in the room? Any questions on Zoom?
I have a question.
Go ahead, Alex.
I don't remember, you might have said it, but I missed what year TESS started being used.
Yes, so TESS and Gaia were launched at the same time, both back in 2018. So this is right around the time I was ending my thesis. So I was able to sort of wrap up what we had done with K2, and all of this stuff with TESS is sort of over the last couple years.
Okay, thank you. Thank you for your presentation. There was a lot of information to absorb in 1 hour, but it's impressive.
I think we see Mark has a question.
Yes, you started out talking about how there's really two methods to determine the presence of these exoplanets. And you've talked to us about the transit method, which appears to be your area of expertise. You also mentioned there was that gravitational shift method. Is there a competition going on perhaps in your field between people that use one method versus the other? Is one method proving to be more effective than the other, or are they just two different ways of skinning the same cat?
That's a great question. So I would say that essentially so both methods are actually used to confirm one planet. So if you see a planet, basically there are different levels of whether a planet is like how real it is. So the first thing that people find usually is to do this transit survey. So you'll find these dips in the light, and usually you can say, okay, this looks like a planet candidate, and that's really good at surveying lots and lots of stars. That's why Kepler was so successful at finding lots and lots of planets. But usually what happens is then after we've found all of these planet candidates, we'll then use these ground-based facilities to do the radial velocity method. So that's the gravitational method that you were talking about. And so that's basically the data that I'm showing on this plot. So these are all systems where we actually already had the transits, which are the kind of little insets that you're seeing, where we saw the planet, the light dropped from the star due to the planet passing in front of it. But then we also got more measurements of the star itself to see that the star was sort of wobbling at the same period that we'd expect based on when we see those transits happening. And so I would say it's less a competition and more like a group effort in that a lot of people in the field are basically using both methods in order to confirm these planet populations. And they tell you kind of different things about these planets. So if you see the light, the light drops of the transits, that's telling you the radius of the planet. But then this gravitational wobble method gives you the mass of the planet. And so by combining the radius and the mass, then you can say something about the density of the planet, the composition even potentially. And so by using both of those methods together, we can get a lot more information on the planet and basically place it in context a lot easier than if we only have one or the other.
Thank you.
Oops. Well, hang on, Tim. Eric, did you have one part?
Well, my question is, what's the current status of Kepler?
Unfortunately, the current status of Kepler is out of commission. So I think as of 2019 or so, Kepler actually ran out of the last of its fuel. and I think right now is just sort of slowly slowing down in its orbit, and in maybe 20 years or so, we'll be crashing back into Earth. But now we're just working with tests.
Okay. Kim?
So with the transit method, does the planet have to go right in front of its host star, or can it come really close to going right in front, right behind?
Did you catch that? Did you catch the question?
Yes, I think I did. So yeah, regarding the, does the planet actually have to go right in front of the star in order to actually see the transit? And yes and no. So basically it is just a geometric effect. So if I just go back, see if I can get there. Here, yes. So basically, if you think of this like diagram as what's actually happening, it is really just you see the light from the star, and then as that planet passes between us and the star, the light that we get from the star is basically just blocked because the planet looks like a black circle, and so we see 99% of that light instead of 100% of that light. And so in order to have that happen, the planet does actually have to directly block the star itself. But we do have some like different orientations where basically the planet just grazes the bottom of the star or something like that, or it only goes through like 1/4 of the star, because instead of going directly left to right like it is on this plot, it goes up to down or something like that. There's some different orientation. And so that can sort of change what we can assume about the star, or what we can assume about the planet, sorry. So if the planet does go fully in front of the star like this, that gives us a really nice measurement of the planet's radius relative to the star. But if we only get a grazing transit, then there's still more ambiguity as to how big that planet actually is. And then there's some other things that we can work out too, which is like the length of time that it takes for that transit to happen can also tell you about the orbital properties of the planet. If you assume a circular orbit for a planet, and its mass and the mass of the star, exactly how long that transit should take. But sometimes we'll see that the transit is a little shorter, a little bit longer. And so that can tell us that either the planet's on an eccentric orbit, or that it's passing over, a strange part of the star. It's not going directly across the center, but maybe over like, one edge or something like that. And so using these transits, we generally, the first thing that we see is the radius of the planet. But there's some other information about the planet's orbit that we can also work out, even if we don't have a perfect transit right across the center of the star.
Yeah, that leads to a joke that I've just got to say. So you're saying that you assume a circular orbit in a frictionless vacuum, right? Got 3 people in here. I don't understand that.
Spherical.
Yeah. Anyway, Steve, did you have a question?
I was just curious if the upcoming James Webb Telescope would have any benefit for you in this kind of research, or is that going to be looking too far back to really see the stars in the life cycle, the time of the life cycle that you're interested in?
I actually have a slide about this, so I am going to bring that up. Yes. So yes, actually, so one of the things that James Webb is going to be really great for these systems is characterizing the atmospheres of these planets. So this is something that we haven't been able to do with Kepler or with TESS or any other telescope at all, because basically, because the stars are so large, they're giant stars, it makes it harder to measure the relative transit depths, which can change in different wavelengths. And so the planet looks like, the size of the planet basically looks different depending on what wavelength of light you're looking at. And that tells you something about the atmosphere of the planet. If there are clouds, for example, they could look really, they could be at one particular height and make the planet look really large in, say, the optical, but then in the infrared, you can see right through those clouds. And so then the planet looks much smaller. And so that's what we actually are hoping to do in the future. And so for the sort of the puffiest planets in our survey, the ones that have the largest scale heights, what we can do is actually use James Webb to do these sort of like transit spectroscopy. So we're measuring the depth of the transit at different wavelengths, as I'm sort of showing at the plot on the bottom here. And at those different wavelengths, we see features of different elements. So basically, for this particular simulated spectrum, we see evidence of water and carbon monoxide, carbon dioxide. And by measuring the strength of those features, we can constrain basically the composition of the planet's atmosphere. So things like, first off, we'll be able to say whether there is water, whether there is carbon dioxide in these planets' atmospheres. But beyond that, we'll also be able to measure things like the carbon to oxygen ratio in its atmosphere. And see, the carbon and oxygen ratio is actually something that's sort of set very early in the planet's lifetime. It's sort of thought to be set by its formation. And so if we can actually measure that ratio, that should tell us like where in the protoplanetary disk these planets were actually forming. And so that will give us more insight as to like how much evolution is happening for these systems. So are these planets that have kind of formed where they were and just kind of hung out, and they're still able to hang out even though the star is starting to evolve? Or is it something where the planets, formed at Jupiter, at Jupiter's orbit, hung out at Jupiter's orbit as the star was, sun-like, but then once the star became a red giant, it now brought that planet that much closer in. And so this is something that we're hoping to study for at least a couple of the planets in our survey to see if we can actually figure out where these planets came from.
Cool. Scott.
Does any of your research inform us at all about Earth's future as the sun floats? Does it help us learn anything about, possibility?
Yeah. So what I will say is, unfortunately, I'm not going to find like the equivalent of Earth around one of my red giant stars. Unfortunately, the precision that we need to do that just doesn't exist yet. That might be something I can do, with new telescopes, maybe with something like James Webb. But I think people would get mad at me if I just took James Webb to stare at my favorite targets for years. And so I think that sort of indirectly it can tell us about the fate of our Earth. So basically, like I was just talking about here, if we can measure things like the C to O ratio and determine where these planets came from, that can also tell us, which planets did they have to, knock out of the way to get to where they are now. And so, for example, if this planet really did form at a Jupiter-like orbit and then moved into where it is today on like a 3-day orbit, that means that any planets that were sort of in between the orbit of Jupiter and a 3-day orbit have been knocked out of their orbit, probably sent into their host star. And so something that I'm really interested in is understanding where these planets came from, but also when they made that move, because that can tell us, how long do we have before we have to worry about things like this on Earth. The bottom line is, it's on the timescale of millions to billions of years. So not anything you or any of your grandkids are going to have to worry about. But eventually, the goal is to see, what fraction of time it takes in the overall lifetime of these systems to actually produce significant migration of these planets, and then the destabilization of whatever orbital systems might have been there before. So my indirect search for planets, or search for like Earth-like planets here, would be to constrain where these hot Jupiters actually came from through this C to O ratio. And then to also see if there are any evidence of multi-planet systems. So if we did find a multi-planet system, that implies that there's more, that's a more stable system, that one planet hasn't knocked the other one out of orbit, or hasn't knocked all of the other planets out of their orbits. And so if we can find a multi-planet system, that gives us more hope for the sort of longevity of these systems. But we haven't found any yet. And so that implies that if you see these systems, they're probably knocking any Earths into their host star before that happens. So I hope that answered your question. That was a long-winded way around. But generally, if we can measure the compositions, we can figure out where these systems came from. And then if we can measure the time scale of that, then we can see how that affects our Earth.
Somebody's already proposed a theoretical way of moving Earth using an asteroid. if we can steer an asteroid that orbits between Earth and Jupiter, we can use Jupiter to pull Earth away using the asteroid. Over multiple orbits over millions and billions of years, it might be enough.
Yeah, like on the time scale of millions of years, I think that's when you have to worry about this stellar evolution. But I think for right now, we're basically safe. One of the other nice things about being where we are in our orbit around the sun is a lot of these effects that cause that sort of in-spiral and circularization that I was talking about earlier are really, really strongly dependent on the separation between the planet and the host star. And so the fact that we're so far out right now means that we're not really going to be affected by that for a really long time. It does mean once it does start to become an issue, it's going to very quickly become much more of an issue. As we move closer in, the forces get stronger and it's kind of a runaway effect. But we have a long time before we have to worry about that.
Cool. Yes, sir.
Have you looked at this rate with any binary star systems with any Jupiter-like planets? And do you find these planets spiral faster and get more circular orbits around binary stars as opposed to non-binary star systems?
That is a fantastic question. So, so far, all of the systems that we've looked at have been single stars. We haven't found any binary star systems. But that's another thing that binaries could very easily trigger this sort of orbital migration, and can also either be very stable or actually trigger instabilities in these planetary systems. And so the fact that we haven't seen any binary systems, I think as of right now, it's still not statistically significant, but it could be telling us that basically any planets that were in binary systems have already been destroyed. And there are some theoretical arguments for how that would happen. And it also depends on the separation of the binary stars, whether the planet's orbiting only one star or both stars, things like that. But yeah, I think that a binary is something that could potentially very strongly affect the stability of these systems. And so investigating the fraction of stars or the fraction of systems that are in binaries, whether they're really wide binaries or much more sort of tight binaries, I think will reveal sort of how stable these systems are on those longer time scales. And if we, of course, do find if we don't find any planets in binary systems, that's a pretty good sign that binarity is actually causing these planets to hit that unstable equilibrium much faster.
Good. Cool. Other questions? In the Zoom session, anyone? Not seeing anything? All right. Well, Sam, marvelous. Absolutely wonderful. Thank you very much.
Yeah, thank you guys very much. Like I said before, it's really cool to come back as now a Mid-Hudson professional astronomer and talk to you guys. Yeah, this is really cool. And hopefully I'll get to actually maybe come in person sometime. My parents are still in Kingston, and so I'm up north every once in a while, and it'd be great to come back to Kuykendall and see things from a slightly different perspective than when I did in high school.
Cool. Love to have you. And don't forget, we have star parties at Lake Taconic State Park and nearest Friday to the new moon. So you keep us in mind for that too. Of course, there'll be voices in there because it gets dark. You can't see anybody, but that's all right.
I also want to thank you, Sam, for presenting tonight. It was amazing to me how much information you gave to us in an hour. Thank you for responding to my original request to come and speak, and thank you for what you've done.
Yeah, no problem. Again, thank you all so much for listening. I hope it wasn't too much of a fire hose of information, that you actually got something out of it instead of just getting soaked with jargon. But no, this is a lot of fun. I really appreciate it. Thank you.
Excellent. Wonderful. All right. With that, I believe I will conclude the October MHAA meeting. Those of us who feel like they want to stick around for a little bit, we would normally chat with our speaker, but he's not here. So
Yeah,
Amongst ourselves, we have to break down our camera equipment, a few of the things like that. And then I suppose those who wish can go visit the diner if we feel like doing that, getting a little cake and coffee. And otherwise, thank you very much. We'll close the meeting and see you all next month.
sounds great.